Okay, so yesterday we left off talking about in an RLC circuit, that there are no power losses in in pure capacitors and inductors, or just capacitors and inductors. And today let's talk about why there are no power losses, and it's got everything to do with the wave nature of this circuit. So the AC voltage source is going to be cycling through the circuit at, say, 60 hertz or whatever the frequency is, and then for every circuit component, namely the inductor and the capacitor, it's going to go through, like for the capacitor, it's going to go through 2 charges and 2 discharges in one whole cycle. So when you take both of those, let's say the positive amplitude waves, and add them to the negative amplitude waves, you're going to get a net zero power loss. And the energy in those waves are basically going to cancel each other out for each half cycle. So in half or a quarter of the cycle, you're going to get charging, and then another quarter discharge, and the next quarter is going to be charged, and the next quarter is going to be discharged. So there's your full cycle. The energy values in each peak and valley are going to cancel each other out, and so therefore there's no net power loss in a capacitor, part of the RLC circuit, and the same situation exists for the inductor. We're going to have 2 cycles of back EMF and 2 cycles where the original current is going to increase in order to set up that back EMF. So there's 2 and 2. Once again, there's no power loss in the inductor. So therefore, in an alternating current circuit, AC circuit, there's no net power loss. So let me just write that up. So why no power loss? So when the current I builds it builds in one direction. Let's see if I can. So for the capacitor, 2 parallel plates, what happens is that, if you look back at the graph for the capacitor, charge accumulates the charge accumulates first, and so therefore the current in that part of the circuit is going to lead the voltage. So even though there's no current through the capacitor is going to discharge after that current builds up. So then you'll have a current running through the other circuit components of the circuit. But basically what happens here, the reason why current is building up, because why current is going to lead the voltage, is because in a capacitor, the charge is starting to build up, and then we get a potential difference after the charge builds up. So we get basically we're setting up a situation for current to take place after the capacitor discharges. But as the capacitor is discharging, or as the capacitor is charging up, that's basically building up current, before the voltage or that potential difference takes place. So basically, at t equals 0, we have maximum charge, and then after that we can have our potential difference. So the current is basically leading the voltage. And how does this even happen when we get maximum charge? Well, current is already going through the circuit. And so now we're building up this charge, and then we'll have the voltage. So current is coming before voltage across the capacitor. Say, you have a line coming in with some current I, you're building up the charge, then you have this potential difference. So that's just a picture of how the current leads voltage. Okay, so as I was saying, so current leads voltage by 1/4 of a cycle, pi over 2. And so we can look back at the graph of the current and voltage with the capacitor. We have maximum current at a time when the voltage is equal to 0. And then as the voltage gets to a maximum, current is going to be at 0. It's going to go from when the voltage is maximum, current is minimum, and then when current is maximum, voltage is minimum. And so it just cycles through, similar to this picture here. So that just keeps on alternating. So we have Vmax, Imax, and we've already seen the equations as to why Imax is going to lead by pi over 2 over the voltage. So again, just to repeat that, current's coming in, builds up charge, then we have voltage. Current builds up voltage. Current comes in first, no voltage, it builds it up, charge is built up at a time when there is no current, there's no current in the capacitor. And then after that, we get a discharge, and then we have current flow and throughout the line, and then the voltage is going to be minimized in that case. So this is a discharge region, and when the capacitor discharges, there's no current, and we have maximum voltage. And then once the voltage goes to 0 within this capacitor, now we have current. Basically flowing in the opposite direction. So we have Imax here, a negative Imax. So it just goes opposite. And then we cycle again, go forward and then backwards, and forward and backwards. So as I was saying before, just to summarize what I was saying earlier, is that the energy within the capacitor is given as 1/2 C delta Vmax squared. So when the voltage is at a maximum, this maximum peak here, we have the maximum energy. And so there's going to be two regions of max energy for the voltage. There's one here and one there, and then we have another maximum voltage in the positive direction and then in the negative direction. So now when we take this energy per time, or this power, we're going to get a net power loss of 0, because these 4 peaks are going to cancel each other out. And that's primarily what's going on there with the capacitor part of the circuit, and why there is no power loss. So again, at t equals 0, we have maximum charge in the capacitor, and the current by which that maximum charge is going to set up is at a maximum, leads this voltage in the current at t equals 0. Something we saw before in the previous chapters. So when it's a half of a quarter of a cycle, rather, Vmax, the voltage is maximized, there's no current. And then at t equals halftime, the current is maximized, and we have no voltage. So we just keep cycling through alternately for both of these quantities. The sum total of everything is 0. So the power loss is 0. So again, the capacitor is charged and discharged twice. So basically the discharging is regions of no charge, add them to the charge regions. If this is 2, this is -2, 0. You know, so that's why there's no power loss. You know, another advantage, another restatement of the advantage of AC circuits. So net power loss, or so no net power loss. Just to keep it simple with the inductors, basically the same thing. I'm just going to draw a picture of that. So let's say that, or just, you know, slight diagram. We have the original current going through the inductor, and it is increasing through time. So that's going to set up a back EMF, you know, this EMF that's going to counter the EMF coming in. And this back EMF is going to create a back current that's going to oppose this, and the current in the circuit is going to decrease. And so as this back EMF is setting up its own current, that original or that induced current is going to create a back EMF to this back EMF. It's basically going to go forward now, and now we're going to get the original current increasing, and it's going to keep sloshing back and forth, similar to what we see in the capacitor, just going back and forth with those changes. So the original current comes in, back EMF sets up its current, and it slows the original current down. And then let's say this back EMF, and the back EMF has its own induced current that slows this original current down. As the induced current increases, we're going to basically get, for lack of a better description, a back EMF. It's going to basically be the original direction of the EMF of the circuit, and it's going to resist this increasing back EMF. This is going to go up, and this induced current is going to go down, and then this original current is going to increase as a result of this back EMF. It's going to basically come back here. It's going to go, this is cycle 1, then 2, then 3, then 4, 1 full cycle. We have no power loss, because there's going to be 2 regions of each, and they're basically going to cancel each other out. If you consider this is positive and this is negative, net is 0. No power loss in the capacitors and the inductors. So basically what's happening, kind of in an indirect way, is that these AC circuits are functioning, at least in terms of the power loss, which is no net power loss. They're kind of like simulating direct current, because they're AC, but the net effect is that the power loss in the inductors and the capacitor being 0, the only power loss that we're going to get is through the resistor, much like a DC. So not a DC circuit, but when we look at how there's no power loss in inductors and capacitors, this circuit starts to act in a purely resistive way, because what's going on in the inductor capacitor gets canceled out, and now we just have the resistor as far as power goes, right? And we'll see more about that in our next section here, talking about resonance. So in 33.7, we have resonance in an RLC circuit. What's going to happen is that the RMS current is basically going to be at the same frequency as the voltage source. And when that can only happen is if both the current and the voltage are in phase with each other. So we saw in the very beginning of this chapter where we had in a purely resistive circuit or resistors in an AC circuit where we had voltage doing this, and then we had current doing, this here. That's what it looks like to be in phase. Even though the current, magnitude-wise, more than the voltage in a resistor in a purely resistive circuit. The important thing here to consider is that the max voltage or max current and max voltage cycle the same way. They are in phase with each other. So their cycles happen at the same time. And that's a picture of what it looks like to be in phase. So the same thing happens in an RLC circuit. When you have resonance, both current and voltage are in phase with each other. The RMS values are in phase because the RMS is the values that we consider anyway in an AC circuit. So resonance in RLC circuit. So a series RLC circuit is said to be in resonance when the driving frequency or the frequency of the voltage source creates an RMS at a maximum value. It's not about looking at the Imax because those peaks cancel each other out over time. The time average is 0. It's the RMS that does not. And that is the quantity that we are that's important to us. The RMS values for current and RMS values for the voltage. So that's why we looked at RMS. So the driving frequency creates IRMS at a maximum value. Well, how does that happen? So let me just set some things up. In general, IRMS equals delta VERMS over Z, and Z, why? Because that's the impedance of RLC, so it's basically the resistance from the R, from the L, and from the C. And Z, the impedance, is equal to R squared plus, so therefore IRMS so we get this value, this equation here. So impedance, so that depends on the frequency. Of an RLC circuit. So, and the reason is because frequency is going to be a function of this XL and XC, and depending on the frequency is going to, produce whatever, impedance is going to be there in the circuit. So R is just going to be R. There is no frequency considerations there. It's all about the capacitor and the inductor because those guys are going to cycle back EMF to original EMF, back and forth, and the capacitor is going to charge and discharge, and slosh, alternate directions in charge. So we can see that the current is going to be positive Imax and then negative Imax and positive Imax. It's going to keep going back and forth within the capacitor, even as the wave of the circuit is driving through. Because we're getting transmission, we're going to have to transmit and I say that because even though we have alternating voltage back and forth in the cycles, positive, negative, there is a progression of this wave, throughout the circuit. It's just within the individual devices, as they cycle, there's going to be an alternation and alternation in voltage, alternation in current, but the overall wave of the circuit is going to proceed, right? And that alternating nature within the inductor and the capacitor can only happen from that AC source that sets it up in the first place. Otherwise, we go back to the previous chapter where we have to open and close switches in order to create that oscillation. So we're creating the oscillation by way of the alternating voltage source that sets up this frequency, this sloshing back and forth in the inductor capacitor. That's why we have inductive reactance and capacitive reactance as opposed to just pure resistance here. And also leads up to the fact that what I was saying before, that the Z depends on omega. And these both have omega terms. So change the omega, you change the impedance by changing the inductance and the inductive reactance and the capacitive reactance is XL and it's XC. Change the frequency. You change that, you change the impedance. So we can say that this omega naught frequency, we're going to see that this particular frequency that would make this circuit resonate, that would make the current, the IRMS and the VRMS cycle together. This particular frequency omega naught, we're going to call the resonance frequency, can only happen where XL minus XC equals 0, or these are equal. Now you can have an inductor, 0.5 Henries. I know Jeremy likes that. Milli-Henries or whatever, previous problem. And we could have a capacitor, 2 picofarads. And based on this omega, we have to alternate this omega such that these guys are equal. Because remember, XL is omega L, XC is 1 over omega C. So we have to get this guy in such a way with these particular values to make these quantities equal. And when you do that, you have resonance. The IRMS will have the same cycles as the VRMS. And that's where you start tuning your radio. There's a particular frequency that we can tune into. Broadcast station, 97.1, 640 AM radio, by basically eliminating the phase difference with the L's and the C's, because if we have, otherwise we have to count for the phase differences, which we do, mostly in a general RLC circuit. But if you want it to resonate, these guys have to be equal. The frequency must be such that these guys are equal and that there is no consideration per se of the what I want to say, the phase shifts inherent within the inductor and the capacitor. So we want to basically cancel this term out in this impedance situation. And so basically, like I was saying before, this circuit starts acting similar to a DC circuit, because in a DC we just deal with resistors. I mean, we deal with capacitors, but in a a purely resistive, easy case circuit, just full of resistors, right? It's just resistor, because a resistor doesn't oscillate. It is what it is. It's no cycling. So that's the point of resonance. We want to get it down to we want to take this RLC circuit and make it as close to a resistive circuit as we can. That way we can have a frequency that we can tune into, and we don't have to worry about the phase shift differences between the inductor and capacitor, because now we won't get one particular frequency that we can tune into. So that's the power of resonance. So these two guys have to be equal. This must be add up to 0. So omega naught would be the resonance frequency. That means that VRMS and IRMS will be in pure phase. Since now, when you do this, sorry about that, when you do this, the circuit will be purely resistive, because we've basically, quote, canceled these out. So that's the idea of resonance. Let me just throw up a couple of power equations here. Oh, not quite yet for that. Let me a few other terms here. Some of the things that I want to write up already spoke on. So we can find that resonant frequency by setting XL to XC, and omega naught L equals 1 over omega naught C. Therefore, omega naught, this will be omega naught squared, right, equals 1 over LC. Omega naught is 1 over square root of LC. If you go back to the previous chapter, we've seen this.
Yeah, we got the same equation.
Well, yeah, we've seen this before in LC circuits in previous chapter, where this frequency, we were just making a substitution, but we come out to this 1 over square root of LC stuff. So we're familiar with this in LC circuits in a non-oscillating case, and the same exists in an oscillating. Well, that's oscillating. We have to force the oscillation by switching the on and off and stuff. But here, this is pure oscillation from an AC voltage source. So we get this omega naught again. This is basically the resonant frequency based on these particular values of L and C. If we can adjust the frequency, adjust the values of L and C to make this frequency, then we can set the reactances equal to each other, and now we have the voltage RMS, the current RMS in phase. We can tune into that 60 cycles, 600 cycles, whatever your radio station is going to broadcast that, we can tune in. So that's all I want to say about that, because I can say a little bit more. I think what I want to do is leave off the power stuff. Well, maybe I'll continue on, because I won't be able to come back to this unless I do some crazy editing. So let me just continue on. So this is our resonant frequency. If you apply voltage, delta V, if that frequency, rather, right? If the applied voltage, I should have written that right here, equals natural frequency of an LC circuit, then we can have maximum RMS current. At that maximum, whatever that is, it'll be in phase with the Vmax. They won't be equal, but they'll be in phase, right? So that's the point. So I think I was redundant here. Let's see if, okay, I will scratch that part out. It's not the same thing. Wrote the same idea twice. So that's what we have. So let me just pause here a second and get back to the rest. Okay, so now power in RLC circuit. I guess suppose in terms of the resonant frequency. So let's develop that. So the average power we've seen, we have this I squared R, I RMS squared R equals delta V RMS squared divided by Z squared times R, V squared over, well, similar to V squared over R times this R. Well, right? Because this is IRMS squared, right? And so we know that Z is that stuff, and then Z squared will, make this whole situation RMS squared times R squared XL minus XC squared, because Z is the square root of that, and then square it. Okay. Since XL equals omega L, C equals 1 over omega C. Omega naught squared equals 1 over LC. The term XL minus XC squared can be expressed as, let's see, all right, XL minus XC squared equals omega L minus 1 over omega C squared. And then we take that through. I'll spare you the tedious algebra there I have on my paper here, and that basically comes out to be L squared over omega squared minus omega naught squared. When we solve everything out, simplify everything, that is our XL minus XC. It reduces to that. So that was what we would put, now in terms of the resonant frequency, we put that in part of our impedance expression. And that in turn makes the average power delta V RMS squared R. As an exercise, if you ever obviously don't have to, you can make sure this reduces to this, but XL minus XC, see it for yourself. This, the original expression that we had, becomes delta V RMS squared R omega squared R squared omega squared L squared omega squared minus omega naught squared. So that would be our average power in terms of the resonance frequency. So, but if that circuit was at resonance, when omega equals omega naught, the average power is a maximum. With a value average power delta V squared RMS over R, which is very similar to our old expression for power, V squared over R, for the DC circuit case. So like I was saying before, when you make an RLC circuit have its current and its frequency in phase, you basically get a DC circuit, DC circuit conditions. And we tune in to that particular frequency that makes this circuit operate this way. Right, because this is similar to V squared over R. One direct voltage source of resistance. And notice that, obviously, resistance never had an RMS or a max. It is what it is. So you're basically having the simplest case of a circuit when the RLC operates at resonance. Then the math bears out. So we can start graphing some of this current versus frequency and power versus frequency data. What we'll notice in these graphs is that the RMS is at a maximum. It starts to trend towards infinity. IRMS goes to infinity as R goes to 0. As you get this thing in resonance, you can play around with your resistor values to maximize, to make that RMS frequency even higher. Lower your frequency, you increase your RMS. So I'm going to graph a couple of deals here. And that just basically comes from the IRMS delta V RMS over R. I mean, it's just simple inverse proportionality. This goes up, this down, this goes up. And that's reflected in these current frequency curves. Current frequency data curves here. Okay, so we have omega is going to be in mega radians per second. Just cycling it pretty fast, and then let's say that this is our IRMS milliamps, and then we go down to 42. Well, we see that there is a rise in, and I say that the resonant frequency here, when we achieve this for a very low value of R, our IRMS is going to be at its max, at a high max at a very low frequency. So we have something that looks like this. Say for this curve, let's say the the value is given here. The resistor is, let's say, 3.5 ohms. Now you start increasing the resistors, the RMS peaks, but steadily lower. And that's R equals 5, and then we have a slight broadening in the peaks as the resistors increase and increase. Larger and larger still. That width, is described as something called a quality factor. The sharpness of the curves. I didn't make these very sharp, but this should have been like very a tall peak. So there's something called a quality factor, which is basically a ratio of the resonant frequency and the difference between the resonant frequency and whatever frequency you had. So basically, if you're not at resonance, it's gonna be oscillating at some frequency. You just couldn't tune into that particular frequency because now there's too much reactance with the inductor and the capacitor, so we can properly tune into it. So at resonance is what we want. So let me write up this quality factor thing, because it's basically quality factors basically governs the width of these peaks, right? So quality factor, just go ahead and write all of this out. The curve sharpness determined by dimensionless parameter called the quality factor, or Q equals omega naught over delta omega, which is your omega minus omega naught. So you can operate at whatever frequency, like I was saying before, but this is a resonance. Here it's not cost effective, especially when you're trying to build a radio station or radio. You're not going to be able to tune into that omega because there's too much happening with the inductor and the capacitor. But the resonant frequency is basically, we are, quote, eliminating the inductor capacitor, and this is just going to make the current and the voltage in the same phase. Also, too, with this frequency here, nothing's in phase. We can get stuff to work, things to operate at any particular frequency other than resonance. We don't have to be in resonance, but this is basically very useful, applicable when you're trying to receive a radio signal from a radio station. Now, at omega naught, I and V are together. So this Q is quality factor determines how wide or sharp, how sharp this is. The width, is determined, is this delta omega factor. So I was confusing the term, sorry about that. So sharpness, how much these guys rise up, I should like to have drawn this a little bit better. Give you a visual idea. So yep, art, my forte. Okay. So a little bit sharper. So these less and less sharp. And let's see, quality factor. Where delta omega is the width of curve, measured between two values of omega. And for the average power, this width for average power, 1/2 of its maximum value. So whatever the maximum average power is, this width is 1/2 of that. And so, again, like I was saying, you want to be at omega naught. Because you want to receive that resonant frequency at your car radio or whatever receiver you have, a transistor radio or radio at your house. You want to be able to tune into the resonance. Last thing, it is shown that delta omega equals R over L. So Q equals omega naught L over R. So I'm not going to write up the radio stuff, but I've alluded to it. I've preceded everything here by saying that, oh, radio station at a resonant frequency, you tune into the resonant frequency. So that is just, one application of all of this. Peak value of power and current at this resonance. And once you get your broadcast or your transmitter at that resonance, then your receiver tunes into that. You gotta, now you have a link up. So I think, depends. I think the last thing we'll talk about today are transformers and power transmission. So 33.8. So it is more economical to transmit power at high voltages and low current. So it's best, in order to do that, to have power lines with high resistance. And the reason why your power station way out is, in the middle of nowhere, is because you want to maximize the situation. High voltage, low current, so that you can minimize the amount of power loss. And the basic reason for that comes in this equation we saw a long time ago, where resistance is rho L over A, and where this is a resistivity. So long wire increases resistance, direct function, and it reduces this current. So that's why, in power station 500, whatever, 200 miles away from the city, and, you have these lines coming in order to maximize this. So by setting this all up this way, this minimizes their power loss. And you want to minimize that. Although AC circuits have basically zero power loss, when you transmit, you want to minimize that over a large distance. And that's the best way to do it, making long power lines, hundreds of miles long, small cross section, high resistivity, or whatever that resistivity factor is going to be, so that at the power station itself, you're pumping high voltage, to reduce that loss. Now you can do the other way, high current, low voltage, because you don't have any catastrophes happen at your power station. Maybe you want to go low voltage, high current, but that's not only is not economical. You might run into risk of disaster with high currents. So this is just basically an agreed upon standard. We want to have our power stations pump out high voltage and use high voltage and low current transmission. So I squared R loss, and power loss. So usually power lines rated voltages of 350 kilovolts or 350,000 volts and 756 kV. Again, that's just arbitrary standard. On the receiving end, now you can't receive this in your house, you blow up. All right. So on the receiving end, it drops down to 20 kilovolts at a distribution station. So you get to this little way station here, and you have what we call step down transformers that'll take this high voltage and step it down to low voltage, and then you step it down even more. Then about 4 kilovolts, I guess, for residences. I guess the transformers you see in your streets, approximately 4,000 volts. And then finally at the residences, there's transformer boxes. Maybe there's other boxes on those power lines, or I'm not sure where those transformers are, but you're going to have a transformer to take this 4,000 volts and step it down to your 120 volts AC that you use at your outlets. So that's for residences. And finally, 120 volts. Commonly in the US, 240 volts, Europe, at your customer site. So how do we do all that? Well, the AC transformer, is a device that steps voltage down. Oh, I'm sorry, I didn't see that question earlier. The transformer is losing energy. No loss in energy. That's what you don't want. So let's take a look at how the transformers work. So we have, like, say, an iron core. It's actually one of the labs at the community college teach at. Iron core here. Say we have AC voltage source, and we have some turns of wire here, and then over here we have more turns. We can have this because we want to take this voltage and step it up. And the more turns of wire, we know that, by Faraday's law, the more turns we get higher voltage. So it's application of Faraday, Faraday's law. Oops, drew that down a little far. So this is going to be a resistor, switch, all that stuff. So this coil here, called the primary, this is secondary. Primary has N1 number of turns, N2 number of turns. And this is, iron core. Point of the iron core is that it increases the magnetic flux, because we're going to get alternating current through here. That's going to set up a changing magnetic field that's going to be, focused within the iron. That magnetic flux is going to come through these turns, is going to create a higher EMF or voltage to be pumped out. So at your power station, you have hundreds of these transformers set up, maybe in series or whatever, however they have them, but there's hundreds of these deals at the power station to produce the voltage on the order of, say, 400,000, 700,000 volts to be pumped out, to the cities. There's a high degree of electromagnetic radiation, fringe effects that can happen at the power station. That's why they're away from everything. Just in case you get a blowout, you're not near any residences. You're not gonna walk outside and there's a power station across the street. First of all, blow everything up. If that blows up, everybody's getting wiped out. So the iron core increases the magnetic flux through the secondary coil. And basically to focus the flux, basically the field. And more turns in the secondary. You have higher EMF. So how do we know that? Remind ourselves Faraday's law. V1 negative N1, changing flux per time. So more of these, and N2, higher E for the same flux because it's the same core of iron. All magnetic field lines, if all magnetic field lines are in the core, the magnetic flux through N1 equals the flux. So flux through 1 is the flux through 2. And so that's why we get the changing flux to be the same, d phi b, right? So that's the same. Voltage in the second, the primary, negative N2, d phi b dt. And if we were going to get the relation or the equation for V2 so that we can design our transformer to maximize V2, well, we can solve for d phi b in N1 and V1 and substitute it into N2 or V2 to get an expression for V2. And that's going to be V1 over N1. And we put that into V2, that becomes negative N2 delta V1. Basically, this whole thing is negative as well. So we just say over N1. And that just becomes N2 delta V1 over N1. So this would be the voltage in the secondary that's going to get pumped out. So we want to increase this for whatever this is and for whatever that is. You know, this is the main idea. That's why in the secondary, in a step up transformer, N2 is greater than 1. We're stepping up the voltage, but in the distribution station, in the power lines you see on the street, you know, those power lines and stuff, those are step down transformers. Step it because you're going to step the voltage all the way down to 120 volts AC at your outlet. It's a question about energy. The idea is that we want to conserve all that. So within any transformer isolated, you know, energy is constant. There could be little eddy currents or fringe effects, some little things that can happen surrounding the transformer. You know, there's never any perfect, you know, conservation, but for the most part, you want to design it to not have any you know, appreciable power loss. When N2 is greater than N1, it's a step up transformer. N2 less than and time remaining. Let's talk about power in a transformer. We know our basic equation for power, I delta V, or I1 delta V1 is going to be equal to I2 delta V2. So we basically want to conserve energy or the net power loss being 0. Right, this is only equal. if or assuming no power loss. There is something called the load resistance in the primary. We're loading it up, basically has its particular resistance, and then there's going to be the equivalent resistance in the secondary. So there's two resistances that we're going to be dealing with. And why do we even talk about such things in a transformer? Well, let's take a look. Low resistance RL will determine the current in I2. All right, so whatever we do in the primary, it's going to determine our current in the secondary, I2. Determines I2. I2 is going to be delta V2 over the load resistance. I1 would be I2 delta V2 over delta V1, because RL is delta V2 over I2. And so basically, or yeah, that's true. But we can, solving for this, yeah, a basic equation here, saying something redundant. So now this is I2, I1, this is all from here. Then that makes, and now we have our expression for I2, substitute in here. And that becomes delta V2 squared over delta V1 load resistor. So that would be kind of like, that would be the current through the primary, voltage squared over the voltage in the primary times the load resistance. And so, and then now, without too much ado, in the secondary we have what is called the equivalent resistance, load to equivalent. As seen, quote unquote, seen from the primary, we have this equivalent resistance. So we go back to, the concept of equivalent resistance. We have current is going to be equal to delta V1 over this equivalent resistance here. Then we solve for equivalent resistance in terms of everything else here. We're going to get the equivalent resistance. So basically, this is the total resistance as viewed from the primary. The equivalent resistance in this transformer is going to be N1 over N2 squared times the load resistance. So basically, application of this. So transformer is going to match the resistance between the primary and the load resistor. So we have the primary coil, and then sorry, we have our load resistance. So load resistance through the secondary coil, and then the primary coil. So this equivalent resistance is basically going to be a resistance match between primary coil and secondary coil. So that's, you know, what we want here. So whatever the resistances are between primary and secondary, that this is the equivalent resistance of this entire transformer. So transformer is built this way. Can match resistances between primary, and load corresponds to the secondary. As we saw, right here. So it's a function of the secondary coil business, that's current over there, and this equivalent resistance is a matching between primary and load, which is basically relative to the secondary. And basically when you have this, you have a sort of kind of resonance called impedance matching. So like this maximum power between the source of power, the AC, and the load resistance on the secondary side, you match that resistance into this overall equivalent resistance. You get something called impedance matching. So you're basically matching the resistances between all sides or both sides of the transformer.
Mr. Kelly, so it would be only one case?
One case. I'm not, what do you mean?
I mean, only in one case, like it will only occur once, right?
No, you can build your transformer to have any type of matching. One case, that doesn't, I mean, you can do anything you want. You can do it for any case. Got it? So this is just the concept behind matching primary to secondary. And so whatever you do on one side, based on this equation, based on this relationship, you know, you can match the resistance on the second side. So you can have, so this causes you to have maximum output. So there's an example where you have a transformer, you know, connected to an amplifier, you know, 1 kilo ohm amplifier and an 8 ohm speaker. You're going to get the maximum amount of power transmission when you can set up your primary and secondary in such a way that obeys this relationship right here. So let's say the primary is your amplifier, the secondary is your speaker. If you can match impedance based on this equation, you have maximum signal, you have maximum broadcast. You can hear your, you know, loud, you know, person talking through a megaphone or your music through this big speaker at the maximum best possible signal if you can match primary to secondary resistance based on this equation.
Yeah, okay.
So that's, you know, you can play around with it. You know, but to your point, I mean, if you just have one type of load and, you know, you can change this number, but, you know, for each case, you can have an equivalent resistance. So yeah, you can play around with it. So yeah, it gives a nice stopping point there. And that's where I actually didn't have any notes on the rectifiers, but we talked a little bit about that. Basically, the last section, rectifiers and filters, let me just summarize it, is basically a way of transforming AC uh, AC voltage or AC current to DC current. So that's the primary idea, because like most of your household appliances we were talking about earlier, most of your household appliances uses DC current. So we want to take that AC, the 120 volts AC, and make it DC. And you can do that by a device called a rectifier. It consists of a diode and a capacitor, resistor and a capacitor. So basically, the primary function of a diode is to take the AC current and have it move in one direction, as opposed to oscillating up and down. It's going to just go in one primary direction. So you're not going to have, basically what that looks like is you're going to chop off part of the AC, and you're just going to have peaks that look like, like that. Let me make that drawing better. So you're still going to have, you just you're using only half of the signal per se. It's going to be something like where this would come down, and then so without too much detail, that's basically what's going to happen. Flows in one direction. This is so-called positive direction. So that's gonna do it. In that off right there.